Okay, so you should be on page 23 of your notes. So really quickly, I'm going to talk about power and work today. Yeah, so we're just going to basically jump right into it. So work is the product, aka way to multiply the displacement of the force and the direction of the displacement. So basically, it is force times distance or force times displacement. All right. So why did I say displacement? Because if you go forward and backwards, we're going to count that as a displacement. Say you go forward. Let's say you go forward this direction to the right 2 meters, and you go back 2 meters. That displacement is going to be actually 0, whereas distance is just 2, right? So 2 meters this way, 2 meters, this would be a total of 4. So don't get too much caught up in that. Just know that energy cannot be negative. An overall system can lose energy, but when I say displacement, it's similar, very similar to distance for our purposes here. So it's basically force times distance. We just use the word displacement because direction does matter. Okay. So the displacement must be parallel to the force. I will talk about that for the equation I'm going to show you in a moment, okay? So the SI units for work, and this is confusing, work is measured in capital J, which is a joule. That is the same thing as KE, kinetic energy, GPE, gravitational potential energy. So this is also measured in joules. So here's a visual I'm going to show you guys. So this visual I have queued up right here. So if we watch this, hopefully it's already zoomed in. And it is. So if we look at this right here, just watch this happening, right? Notice that as all of these are going to equal 8.82 joules of energy, no matter the angle of that ramp. However, it becomes less force is required on the first one on the far left here because it has a longer distance to go. Okay, so if you look at this one right here has 0.9 times 9.8 because the work is 8.82. Now notice on this one here, it's more force, but it has to travel less distance until it gets to the top here. Okay, but notice the work is 8.82, 8.82. Now the last one, we have a force of 17 newtons. The displacement is less than the other one, right? But the work is still the same. So that's an important thing to think about when we talk about this with work. All right, so just kind of showing you that graphic there. That should make sense in a moving truck, why those ramps that come out are so long. They decrease the amount of force you have to use. So you can go up and down. You just got to carry the weight of the box, not the weight of the box and straight up, right? That's what makes it more difficult. So back to this. And remember, when we talk about this, force in newtons, displacement in meters. Now you could say distance as well, but it's a little bit slightly different. Just know that distance displacements, one's a vector, one's not, right? So displacement's a vector, but can you have negative energy? No, you cannot have negative energy. Violates the law of conservation of energy. A system can lose energy, but yeah. So this is like the graphic I just showed you a second ago. With that, notice the force on this, right? The force becomes more as it becomes steeper. That should make intuitive sense, right? So as this becomes less steep, I have a longer distance to go from here to here, right? But the force becomes less. As it becomes more steep, right, the displacement becomes less, but the force it takes to go up. That should hopefully make sense. The work remains constant on these two. As the force increases, the displacement decreases. So the distance you have to travel decreases as the force increases. That's called an inverse relationship, right? Inversely proportional. Okay. So now what I mean by this, I'm going to show in another slide. The force and displacement must be parallel. So all of these in this example are parallel. So I'll show you why in a moment. Because when I talk about cosine of theta, if I'm using degrees in my, and I'll explain this in a moment. The angle between the force and the displacement, that's theta. So in this example, theta is 0 degrees. If you're like, what are you talking about with that, Mr. Smith? What does that actually mean? How are they parallel? So I'm going to show you that in the next slide. Now, if you put this in the calculator, though, the cosine, if your calculator is in degrees, if you put cosine of 0, it equals to 1. So anything times 1 is going to stay the same. So since this would be 1 if it's parallel, it's just force times distance. So introductory level physics, we typically just leave it like that. So the next thing, I'm going to show you why this is 0. So if I look at the force and displacement here, they're stacked on top of each other. They're parallel. So notice these arrows are right on top of each other because the direction you're going and the force you're applying, you're pulling it up, is going to be the same. So if I look here, that's going to be 0 degrees if I measure with a protractor, right? So 0. So I did the first problem here, 9.8 times 0.9. So all of these, right, the distance or displacement is going to be changing, but this is going to be 0 on all of them because they're parallel to one another. They're right on top of each other, stacked. So hopefully that makes sense. So cosine of 0 is 1. So my example problem, a lab cart that weighs 300 newtons is lifted to the top of an incline 2 meters long. What is the work done by the cart? So first thing we do is identify our variables. So this is a force, right? You could say, if you want to be really one, F of little g, if you want to be more precise on this. So the distance or displacement is 2 meters long, right? What is the work done by the cart? So W, and that's work, guys, measured in joules. So force times distance, and I don't have any angles in here, so I'm assuming that the angle is parallel. So it's just 600 joules. So the next question on this is what you should have written down, right? How much force would be required to lift the same cart, so the same height, using a 10-meter long ramp? So this time, we're just going to change. We want to figure out the force, how much force. We know the displacement now is 10 from here, right? The work done will be the same. It's going to be 600 joules. That's not going to change. So what we have to do, we have our equation. We have our variable. So we just plug this in. So 600 joules equals force times 10. So divide both sides by 10. These cancel right here. So 60 newtons. So obviously it's going to take, if you look at the force here from the previous problem, the first problem said 300 newtons. This now is going to be 60 newtons. So it's going to take a longer distance to push it, but it's going to be a lot less force. This is like introducing the concept of mechanical advantage. So last one, it's kind of a trick question here. A waiter applies a force of 150 newtons to hold a tray filled with plates on his shoulder. He then moves 7 meters towards the kitchen door. What is the work done by the waiter? So first thing we do, we'd identify our variables, right? But this is kind of a trick question. I just want to explain the logic. The waiter does no work on the tray because the force is vertical and the displacement or distance is horizontal. You're like, huh? So the force in this is 150 newtons, okay? The distance is 7 meters, but really that's the displacement is 7 meters. Now, here's the kicker on this. They're 90 degrees from one another, horizontal. So if I do this in the equation, 150 times 7 times 90, so if you take the cosine of 90, if you're in degrees mode, it's always going to give you 0. So 0 times anything is 0. So if you're confused about that, look at this graphic I just added this year. 7 meters, I'm going this direction towards the kitchen door, right? Horizontal. The force is being pushed up here, okay? So this angle of theta in this case is 90 degrees. So that's why the work, so if you put cosine of 90 in the calculator, it'll give you 0. 0 times anything is 0. Okay, so that's the introduction into work. The next thing we're going to jump right into is power. This is a little confusing for students, so I want you to understand this. Power is how fast you do the work. So if you think of we'll talk about that in a second, but yeah, the equation is work divided by time, how fast work gets done. But anything you have in joules, any equation that's given to you in joules, you could put in here. Because remember, work is measured in joules. So if you have joules divided by time, you can figure out the power. So joules divided by seconds, you're more familiar with this term, or watts, okay? So a watt is in Moodle is capital W. Why is it capital? It's named after a human. And then joules per second. So a horsepower is a type of power. 1 horsepower of an electric motor is equal to about 750 watts. So a 50-watt light bulb, a 100-watt light bulb doesn't burn, it converts, I shouldn't say burns, it converts a 100-watt light bulb, uses 100 joules of energy per 1 second. So obviously you want the lower the light bulb, the more energy you'll save, right? So Tomas runs up the stairs in 24 seconds. His weight is 700 newtons, and the height of the stairs is 10 meters. So what is the work done by Thomas to get to the top of the stairs? So identify our variables. His weight, 700 newtons. You could put F a little g here. I wouldn't be angry with that. Displacement is 10 meters. So the work, I'm just going to use that old equation, right? So we'd use this first. All right, so now we're assuming the force is parallel, right? Unless it's said otherwise. So the amount of work is done is 7,000 joules. Now, how much power? So you should have this all written down, right? The power is work divided by time. So we just plug this in, 7,000 divided by 24. So that gives me 291 joules per second, or 291 watts, capital W in Moodle. Okay, so that's how much power you must apply to do this task. So a student weighs 700 newtons, climbs a flight of stairs at 7 meters in 8 seconds. How much power does he need to do this? So same idea, okay? 700 newtons, 7 meters is my distance, right? That's my F of little g, if you wanted to, near newtons. Your displacement, 7 meters. You have 8 seconds. So it's just, we have to figure out, right? We don't know what the work is. We can calculate that. Work is force times distance. So to figure this out, it's force times distance. 700 times 7, right? So that's here. So then I divide that by my time, right? Because this goes right here. Where students get confused with this is a unit on how you measure power. This is work, this is work. So work is measured in joules. Power is measured in watts. These are not the same thing, guys. Watts, work. Watts, work. Watts, work. Get that sorted, right? Power is measured in watts, aka joules per second. Maybe it's easier if you just keep it at joules per second. But if you see the word watt or 12, like something like that, you're going to think that is power, right? So anyway, thanks. That's it.